All right, everybody. Today's meeting, I want to discuss two concepts. These are the topics of causation. One concept is causal discovery, and the other is causal inference. So, causal discovery is when we try to understand if there is actually some type of causal structure or some type of relationship between variables based on patterns that we see in the data. And causal inference helps us to understand or hypothesize and better understand the causal structure. And we want to estimate the effect of one variable on another. Okay, so we want to look at the impact of perhaps a marketing campaign on sales. If we put more money into marketing, or which marketing campaign, A, B, C, D, E, F, W, X, Y, Z, what impact is that going to have on sales? Okay, so you actually specify the treatment, the outcome, and other common causes. So in the first instance here, causal discovery, we don't know if there's a relationship between variables. With causal inference, we know that there is a relationship because we determine that using causal discovery, and we want to better understand what that relationship is. Okay, so I have some sample data here. I don't have actual marketing data. I guess I could have Googled it, but doesn't really matter. I just want to introduce the concept and yeah, I just didn't have the data. I thought it was just easier in this case just to create it dynamically. Okay, so we're using the similar common Python libraries that we always use, NumPy, Pandas, but we're also using a new library here to do causal discovery. This is called DoY. Okay, and this is going to produce a causal model for us. So we're generating the random data right now. We're going to look at three variables here: campaign, advertising spend, and then sales, right? So we want to understand, is there a relationship between these variables? And if so, what is that relationship? So here in displaying the data frame, you can see the outcome here. So we have the campaign, the spend, and the ultimate sales based on the spend and which campaign we're looking at, either campaign 0 or campaign 1, right? It's a binary outcome here. So we're going to use causal discovery to see if there's actually a relationship here. So we're going to also use network graphs to plot and to display the results here. So I've got a couple other videos on network graphs. I think these are very fascinating types of tools, and you can do all types of things with these causal graphs, right? Anything from creating a recommendation engine to doing clustering to doing classification. Of course, there's other algorithms specifically designed for those types of scenarios, right? But these graph matrices are pretty powerful, right? There's all kinds of applications for these things. So I'm going to go ahead and share this code with you. I'm not going to go through all the details here, but suffice it to say, we have our network libraries. The G variable is helping us to create the adjacency matrix, right? And we're adding labels. So I've got other videos that dive much deeper into network graphs. So if you want to check those out, by all means, go for it. So I created the graph here, and I'm printing the results. So this is what it looks like, right, when it's displayed. We're looking at the advertising spend. Apparently, the D got cut off here, but this is supposed to be advertising spend. You know what? Let me refresh this just so you can see that this is actually working code, right? Then just like copy and paste it and paste in an image or whatever. Right? I'll share all this code with you so you can run this in your own Jupyter notebook environment. So this is great. The cell just refreshed. And we have the outcome here. We have advertising spend and the impact on the overall campaign and the impact on sales, right? And the relationship between sales and the campaign. So I put together some notes here so we can understand what is this graph saying, right? And interpret the results. So the advertising spend to sales and the advertising spend to campaign, right? The arrows indicate that the changes in advertising spend are believed to influence or cause changes in sales. And that would make sense, right? If you're spending more on advertising, your sales should increase. If it doesn't increase, something is probably wrong there. And if it actually decreases, like if you increase your advertising spend and sales decrease, something's definitely wrong there, right? So you have to look into that. So increasing advertising spend should have an impact on sales, right? The sales can be higher as we spend more on advertising. This shows us that there's a cause and effect, right? So I have a couple other videos on causation too. That's what we're trying to measure. Is there a cause and an effect, and if so, we want to know what that is, right? In a lot of data science, machine learning, you never see the cause and effect. You're looking at making predictions into the future based on historical events, right? So cause and effect analysis is kind of different. I think this is actually pretty fascinating. So that's what we're looking at in this scenario, okay? So as advertising spend, um, there's also a relationship between advertising spend and campaign because we see the arrow going from one to the other, right? This indicates that advertising spend may drive the campaign, right? And one thing to note that's interesting here, the direction of the arrow or the length of the arrow really doesn't have any meaning. So it's kind of arbitrary. I looked into this. It's not like as you have a longer arrow between advertising spend and campaign, then you're spending more money. It's nothing like that. But there is a relationship between advertising and campaign and advertising sales, right? So there's also a relationship between sales and campaign. The short arrow, again, the length of the arrow is insignificant. It's kind of arbitrary in this case. This arrow indicates that sales could influence the decision to run a campaign, right? So as sales are increasing, your campaigns should be increasing too, right? Because it's driven by unidirectional here. It's not bidirectional. It goes from sales to campaign. If sales are high, the business might decide to invest more in marketing or promotional campaigns to capitalize on that success. And this creates a causal relationship that could suggest strategic business decision based on sales performance, right? So there's the cause and effect. Now we know, because of our causal discovery exercise here, that there is actually a relationship, and we want to understand the causal inference, okay? So this model is going to help us understand that. If you look closely back here, we create the data frame, and we fit the data into an LiNGAM. Okay, this is a DirectLINGAM, and we're producing a matrix. We're doing network analysis here. That's what this library is for. And then we're printing out the results. Okay, that's this print right here is this. Okay, I put a small dotted line to separate that, just to indicate that there's a difference, and we're plotting the result. But if you look closely, there's really no model that we set up that we're telling the computer what to do, right? We're fitting the model, but we don't know if there's a relationship at this point, right? So we can't determine that. But that's what causal inference is going to do. So now we set up a very different model. This is a very, very generic model. If you go back here and look closely, this LiNGAM model is just taking everything, we're dumping everything into the model. We're dumping everything into the model, and it's telling us is a relationship. Now we know there's a relationship, right, between the different features. So we're creating a model, and we're telling it what is the data. We're feeding the data. The treatment is the campaign. The outcome is the sales, and the common cause is the advertising spend. So these models are very different. Over here, you have a very general model, right? That's actually you're not directing the model what to do, right? The model is trying to determine if there's a relationship, and there is, right? Now we know what the relationship is. So this model is a little bit more sophisticated, where we're doing a little bit more work and customization here, because we're specifically telling the model, okay, this is the treatment, the outcome, and the common cause. So again, the model is going to run, and we're going to plot the results. Okay, we can see that right down here. So advertising spend the campaign again, advertising spend the sales. We can see that again, and campaign to sales, just like we saw in the first model, right? Oh, sorry. And the first model is actually sales to campaign, right? That was the direction of the arrow. Here we have campaign to sales. Again, the length of the arrow is insignificant, or it has no significance at all. But the direction of the arrow is very important. It says it's going from one node here to another node. So from advertising spend to campaign, advertising spend to sales, and campaign to sales. Okay, let me refresh this here. Try to get rid of those little error warnings. It's kind of annoying, and I plotted that into I plugged that code into the model here, and said, please drop out all those warning signs. Oh, I guess they're going now. Okay, I think it's fine. It's fine. Something didn't refresh. Okay, So we got the results. We have the plot. So we know that there is a relationship, and we can tell which variables are affecting which, right? That's the causation right there. So it's pretty cool, right? Again, the changes in advertising spend drives or influences the campaign and sales, and similarly, campaign causes changes in sales, right? As you change a campaign, you have different types of campaigns. Sales are going to fluctuate up and down, right? So we can go ahead and test the legitimacy of this model. This is a standard ordinary least square linear regression model that we're going to fit. So we have the independent variable advertising spend, and then the dependent variable, this is the independent variable, and then we're adding in a constant term, and then we're going to go ahead and run this linear regression model and get the outcome. So r squared 0.477, adjust r squared is pretty close, a little bit lower. It's always lower, right? When you look at the adjusted r squared, and you have some statistics down here, the t statistic and the p-value. Okay, so I have some notes that's going to help us understand what's going on here. The r squared is the value that indicates about 47% of the variance in sales can be explained by advertising. That's kind of weak. You really want to see more like 70%. You want this number to be 0.7 or greater to be statistically significant. Right now, this could be almost accidental or incidental. There's no real relationship between sales and advertising spend, or spend driving advertising sales, right? The relationship is just too weak over here. And that's fine, right? The data is what it is. So this model is just explaining what's going on. Okay, the F statistic tests whether at least one predictor variable has a non-zero coefficient. Okay, a p-value less than 0.05 is good. The lower, the better. Here's the p, 0.024 for the constant, and the advertising spend is actually 0.000. So that's very low. That's very significant there. Anything less than 0.05. That's going to be more appealing to us, right? So the model shows a relationship between advertising spend and sales, but again, it's not a huge relationships. If you go back, I can tell you why. Because it's kind of random, because we're just using random data. This is not real data. It's just made up data that I came up with. Again, I don't have this advertising data, and I didn't really spend a whole lot of time Googling it. I could have, but I just thought it easier to just explain the concept here, just to create it on the fly. So that's what I did. And you can see there's no real relationship here between advertising spend and sales. There is a slight relationship, right, indicated by those arrows, but statistically it's pretty weak, and it's just randomly made up data. That's why. So if you do this with real data, you'll most likely have a stronger relationship, but maybe not. If it's under 0.7, you could be spending a lot on your advertising, and the sales could be pretty weak, and you're basically just wasting your money, right? That's why we're looking at this R squared number. That's very important. So the coefficient of advertising is positive. The low p-value is indicative of statistical significance. However, the R squared is pretty low, 0.47, 47%. 47% is explained. Oh, wait, that was unexplained. That was right. What is it? 52.3% is unexplained. X-P-L-A-I-N-E-D, unexplained. So 47% is explained, 52.3% is unexplained. So let's look at another scenario of causal discovery and causal inference, and then we can call it a day. We'll see, similar to before, we're creating the data frame. Slightly different scenario now. We have features, price, and satisfaction. So again, we're fitting the model. We're not specifying what the inputs and the outputs are. We're just telling the model, just look at all the data, and you tell me, is there a relationship between the data? Because remember, causal discovery, we're discovering if indeed there is a relationship, or if there is no relationship. That's what we have to determine. And if there is, we can proceed with the causal inference, which tells us what that relationship is. Okay, so let me refresh this here. Control Enter. Okay. Whoops. Okay, I did not refresh this, so we got kind of the same scenario as before. That's the problem. I named this data frame as data, and this one was called data 2. So I just hacked this together pretty quick. So in the real world, you would say like data sample 1 or data advertising, right? If you name the variables the same, yeah, you could have these kind of weird outcomes over here. And this could probably be have a better naming convention. This could be data for price and satisfaction. Right? So you want to make these significant and meaningful. If you don't do that, I've seen a lot of people just call things data, data one, data two. Don't do that. I'm guilty as charged. This was just a quick thing I threw together, but yeah, that's what happens when you get lazy, right? It comes back to get you. So we're plotting and charting the results again. We can see a relationship between price and feature and price and satisfaction, and there's a relationship between satisfaction and feature. Okay, so we know what these relationships are for the causal discovery exercise. Now we can go ahead and do the causal inference, and we'll set up the model with the data, just like before. The treatment is going to be the price. The outcome is satisfaction. Okay, hopefully that makes sense. As you increase the price for this experience, it could be, I don't know, maybe a cruise. Like my family and I are going on a cruise in December. If you pay a higher price, you should have more satisfaction because you're going to get more items on the cruise. You can go to the better restaurants. You can do all kinds of fun things that you're excluded from if you take the more basic package, right? So that scenario, this is just a very generic scenario, but that could be true there, right? And the common cause could be the features, right? So we know this relationship. Let's refresh this, run the model, and see what the outcome is. Okay, so before, in this view over here, we're looking at causal discovery. Now we know this relationship. Let's see what the relationship is. This causal model will tell us that. There is a, looks like the feature drives the price, and the feature drives the satisfaction, and the price drives the satisfaction too. Okay, so let's go down and rerun this model, Control Enter. Okay, now we have a nice R squared, 1.0. The F statistic is very high. The higher, the better. The p-value is very low down here, right? 0.0, and the t statistic is very high. So these are all statistically significant. So these are some pretty awful numbers. R squared says that 100% of the variance, and the dependent variable, which is the price, is explained by the independent variable, which is satisfaction, right? So this is the dependent. This is the independent here, right? So satisfaction. And wait, let me see, was that right? Price. The dependent is price, right? I'm sorry, the independent is price. Sorry. Got that mixed up a little bit. Okay. And no, I'm sorry, take it back. This is a dependent right here. Dependent is price. The independent is the constant, right? So do the price. Wait 1 second. Did I actually do that? Hang on. Price satisfaction. Let me look at the other example I had here. Did I actually do it wrong? AdvertisingSpend. Oh yeah. Satisfaction, right? Okay. Sorry, I just caught a mistake. Okay, let's fix it. That's why it's 100%. Okay. Okay, so this is totally different. So I had a mistake there. It's measuring the dependent and the independent. So of course it's going to be 100%. So the R squared is actually 0.13. So that's pretty low, right? So 0.13. The F statistic is 149. So that's kind of high. The p-value is pretty low here, so that looks good. So there is a statistical significance here, but the t statistic is actually negative. So this model is doing what it's supposed to do, but the data is not going to help us make very good predictions here because we have a very low R squared. 0.13, this should be 0.7 and higher, and this should be positive, and at least I think the cutoff for this is 1.96. So the p is low, that's good, but all these other metrics over here are not helping us to understand that this model is not going to make good predictions, right? It's just not the right kind of model. Again, the data was generated randomly. Okay, if you go over here, right, run data. I didn't have the marketing data, so it would be more helpful to have. When you create random data, you get some funky results, but I think it's okay. I wanted to test the model and see what the outcome was. The real purpose of this whole experiment was to look at causal discovery and causal inference, and that is mission accomplished, right? We did that in 2 scenarios, but since the data was a little bit funky because it was made up and it was just random, ultimately the model is not going to be able to make good predictions. And that's fine. Okay, this is not a video about OLS regression models. It's about causal discovery and causal inference. So, I'm going to update my notes, and then I will share this file with you so you guys have all the source code. Okay, I do that with all my videos. I always share the code so you guys can copy and paste it and run this in your own Jupyter Notebook environment and learn in the process. I think when you get your hands on the keyboard and start doing these types of exercises, you can learn a ton. If you just watch the video, you're not going to learn as much. It's like reading the book about data science, but not practicing any of the experiments in the book, just reading and then getting to the end. And you think you learned a lot. I bet anything, you probably didn't learn a whole heck of a lot, right? You really have to get your hands dirty, roll up your sleeves, and actually do the stuff. That's where the learning process really kicks in, right? So here's my notes on causal discovery. I'll let you go through that. It's pretty comprehensive here. I don't want to just read off the page. Everybody here is smart and competent. You can read for yourself what it's doing. But yeah, I did go more into depth about what is causal discovery and what is causal inference. So you can read that at your leisure. And that pretty much wraps it up. Hopefully you guys learned a ton. I've learned quite a bit when I was putting together these scripts here. I will update my notes because this is not accurate now, but I'll go ahead and make these changes. Then I'll share all the code with you guys later today. Okay, again, hopefully this was a worthwhile effort. Hopefully you learned something today. I definitely learned a couple new things and filled in a couple personal knowledge gaps I had when I was working on these scripts. Okay, so that's it. Thanks for your time. Enjoy the rest of your day. Goodbye.